So here is Klondike from above. Now this system has on average anywhere from 30 to 120 gallons per minute. It's seasonal, of course, affected by rain. Seeps coming out at about a 4 to 5 pH, then drops quickly, and it's ferrous I don't believe there's any alkalinity available in the system at all, or at least below non-detect. And that by the time the water gets to the MRU that we put in place, the pH is stabilized and it's dropped down to around a 3.3, 3.5, 3.2 within that range. And the concentrations of iron are still somewhere around 80 or 90. So we actually have lower pH at this new site, and it's more consistent, which is great. And also we've got higher concentrations of iron. So we're thinking, hey, great, now we've got even better conditions that'll encourage the self-selection of these litho and chemo, or the litho, auto, and heterotrophs. And there was plenty of iron schwertmanite already within the system as well. So, you could already see it coming out. All right, this is perfect. Let's go ahead and lock this down, see how we're going to use this larger tank. Whereas the first two units combined were 1,500 gallons. The Mark 318 is 1,800 gallons by itself within one system. So it has fewer oxygen turnovers. There are fewer cells or fewer steps in total within this system, with 3 versus the 6 in the 2015 and 2016 systems. So the overall system, this is a diagram of how it's been put together. Now, the MRU is actually right here in the system by where it says KL1-P3, not where we've got it up here. So there is a long oxidation pond of about, I'd say 70 something or other feet long before it gets to the box. So you've got the original seep all the way up there where it says Weir 32R2. That's where it's coming out 4 to 5 pH at about 120, 100, in some cases up to 150 ferrous. And then it begins to oxidize, and that's where your pH rapidly drops through these the first portion of the system before it comes to us. And we were shooting specifically for that low pH. That's what we wanted to work with because it was more consistent with what we'd seen at the other sites. After that, it goes into 2 long oxidation ponds, and I don't know if I'd classify them as ponds. They're more or horizontal flow wetlands, about 40, well, I'd guess about 30 feet wide, about 80 to 90 feet long, and then maybe a little bit long, and total depth of about 6 inches or so. So oxidation, there is certainly precipitation of schwertmanite within that system as well, but it's in a 2-dimensional form, not the 3-dimensional form that we have with the MRUs. So here you can see the one MRU put into place, and by the way, there's the influent pond you can see here, and the influent pond right there to the right, and that's a vertical flow wetland of saps. Successive alkalinity producing cell, alkaline, or good old-fashioned limestone. So this system is good. They tried to get as much iron out as they could, low pH, and then settle that material out before it went into the saps. Now this system was unfortunately having breakthrough because it needed maintenance. It was about 8 to 10 years old by the time I came onto the system here. Looked at it the first time a year or two ago. And it needed a little bit of updates, needed some maintenance. There was a breakthrough where some water was going straight into the sap. Raw water was going right into the sap and was precipitating right there and was causing backup. The system wasn't working as well as it could have been. So with a little bit of assistance from Slovakovsky as well as AMD Industries with Bill Gongleware, we were able to take care of some of those breaching issues and get the system back up to par. So now initially we wanted this system about 4 inches lower, 4 to 6 inches lower, because as you can see, that pipe coming off the side, there is not a whole heck of a lot of drop. And unfortunately, as the first cell began to back up, because that's what it does, it's going to create hydraulic pressure, that it actually backed up the entire pipe as well, all the way up to the point where we were gathering the water from the pond. So we didn't have near the flow rate through this system that we'd wanted to. Based off the data in the past, a reactor of this size should be running about 90 gallons a minute to get those same removal and loading rates as we had seen from Squatter Falls in 2016. But hey, you work with what you get. We had a machine for a day. That's what happens. But we've had anywhere from 10 to 50 gallons per minute flow through on this unit. Of course, like I said, if it was a little bit lower, we would have even better flow rates. And in we've been continually making adaptations into this system. Like we're going to be putting in 6-inch influent pipes, where if we can get the water running through a larger pipe, we'll be able to get even more flow through it. Whether we'll ever get up to that 90 gallons a minute, I'm not sure. But we're pretty happy with the numbers that we're seeing so far. Let's one moment, please. Kind of have some things being hidden here. First large system manifold was this system. So some of the adaptations, new things that we did on this system was the full manifold, allowing each one of the individual cells to be emptied out and then refilled, and which makes the cleaning and the maintenance of this mineral form, which is pretty dense and heavy over time, much easier. And just recently then also we started doing direct injection using small gas powered pumps into the bottom of the system to pump 250 gallons a minute through the system, or probably closer to 200, to really get a good solid cleaning of the system. Because yeah, we're pulling iron like gangbuster, but you got to be able to clean that out too. So it isn't just, do you have a great bioreactor? Is how easy is it to clean the system? That directly impacts what the long-term maintenance operations and maintenance is going to be on those systems. Now going back to it, I had mentioned earlier, so this is the same numbers from the second study with the true MRUs, that based off of this flow rate, based off of this volume, that if we've got 75 gallons a minute at 20, then I did the numbers, 1,800 gallons a minute at, 1,800 gallons volume at 20 minutes of residence time worked out to 90 gallons a minute with this 1,800 gallon system. So that's what we're hoping to achieve, something close to. Let's see. So based on Squatter Falls, like I was saying, really should be running around 90 gallons per minute for the system. But in emergency overflow, this system, then that unit will handle about 200 gallons per minute. So if you get a flood or a storm that comes in that really hammers the system, you're going to pull up to, you'll be pulling iron up to that 90, maybe 100 gallons per minute. And at that point, then you're going to get overflow, but then that's going through the overflow on the weirs. I can actually show you the next cell or the next picture. And here is a system. This one was running at about 120 to 150 gallons a minute or so. And the coir was actually beginning to get in the way of the overflows. Now we've since done adaptations that allow us to put trays over top of the coir and keep it in place. And that handled a lot of the issues, so that when you do get a really high flow that's more than that unit can handle, just goes right over the top of the treatment cell, but it doesn't stop the treatment in that cell because there's still water going down through down the delivery vault into the into the sludge vault, which is at the bottom of each one of those. It's a holding vault for sludge, and then comes up through the treatment vault itself. So you still get treatment, you're just not going to get all of it. Let's see. Now this had come from Art was very kind. Malcolm Crittenden with PADP was good enough to lend us a DO gauge. And for the first time in a long time, we were able to do some quantifications. Art was able to do some quantifications on what the actual DO saturation was. And this, by the way, this is going to be up on YouTube later on, so you'll be able to go back and review. But Art was able to find that with that DO probe, and he wanted to do some more calibration. We're going to do some more work on it as well. But we were showing that 81% coming into the first unit, the first cell at the treatment or the delivery vault. After it came up and through the first cell, 71% saturation. And that unit, then I do have to say that that system at that time was just about to the point of full plug flow, and it was backing itself up to start going over the weirs. It hadn't fully achieved that yet, but that cell with all the coconut coir, most of that surface area had been taken up. Now, and always remember that whatever the leading cell is, that whether it be the first cell or the one that is the first one that isn't in overflow, that's the cell that's always going to be pulling the most material out. So we had 71%, 69%, then 65%. So we see dissolved oxygen saturation dropping from cell to cell to cell. Now we want to go over this a little bit more in detail, but what that says to me is that we've got more BOD and COD being consumed from cell to cell to cell. It's not a bad thing. Oh, hey, okay, maybe dissolved oxygen is another decent proxy for the treatment rate in each one of those cells, because something's chewing up that oxygen. And if there's more iron being removed cell to cell to cell, at the back end, there's still more surface area to work with, and there's greater capacity to pull out more material. And I think we may be seeing that as a proxy here in the dissolved oxygen rates. And of course, Art is on board here too. Please, anybody, if you want to ask Art any questions, feel free. No problems there. Let's see. So moving on. Okay, I got a video. And this is.
I did the first tank 2 minutes ago, 2.5, maybe 3, or the first cell 2.5, 3 minutes ago.
See that.
So fully empty the whole box out.
Oh, here, let me start that back over again.
Just wanted to show you the flush process. Nothing fancy, really. I do want to point out that this is specifically a Schwartmanite coming out. This isn't a ferric oxyhydroxide made out of circumneutral solution of the AMD. Wanted to point out how quickly it drops, falling out of the water column rapidly, and I just kind of thought that was neat because maybe a benefit for using low pH iron oxidation, forming a more dense mineral that will then precipitate on its own without the need for any flocculation. You can sort of, I don't know if you can see the leading edge right there. That's about as far out as I can see it since I popped the valves. And see, I did the first tank. Well, here's a much better vantage. So it's pouring out from the bottom and going into a cloud. See how quickly it starts to settle out. Good argument for not needing flocculant. Get most of your iron out, immediately precipitates. Well, not immediately, excuse me, but comes out pretty darn quick compared to standard precipitation. Gravity settling, I should say.
Okay, yeah, just wanted to show you that really fast. I'd done that here just a couple weeks ago. And that was when I was still just doing the stir and drain. And since then, we've started doing injection of water into the bottom. And I think I'm just going to go and adapt another manifold on the other side so that you can run water straight from one side straight through to the other to more effectively clear the sludge vault. Because if you can get all that stuff out that much easier, then you've got that much more time in between maintenance returns. So right now we're doing it somewhere around 3 to 5, about 3 to 4 weeks to do a drain, because if you don't, it's pulling out so much material, on order of several kilograms a day. If you don't get back to it, it's going to start plugging itself up in that first cell, and you're losing some of the overall treatment. Now, if you've got multiple boxes in a row, who cares? If the first cell or the first couple cells plug, the primary, that leading edge, whichever the one is that isn't overflowing, that's the unit, the one right after, the cell right after that, that's the one that's pulling most of the iron. So it's still okay. You're still going to be pulling a lot of material, and then it's your decision on how often do you want to come back for it. It really becomes this trade-off, like, all right, you're going to put in more boxes up front at a greater addition or at a greater upfront cost for construction, knowing though that you're not going to have to come back as often to clean it out. So then where it goes back and forth for your decisions of original construction costs versus long-term maintenance costs. And those are all choices that are made by the check signers. Let's see. So Athena's then, she was able to determine, and I apologize, you're not ever supposed to do lots of words on a cell, but I just wanted to get it out there, that Athena was able to characterize when she took samples from the site. She took them up to the MCL. Once again, she found quartz, kaolinite, muscovite, goethite, and schwartmanite using XRD. Now, Art would like to hold off for right now before we have more data sets and some winter weather before releasing data, and I'm fine with that. But I can say that the rates so far are consistent with what we'd seen at Squatter Falls. The one rate that I saw at around 30 to 40 gallons a minute was something on order of about 650 grams per cubic meter a day, which in this box works out to like 2.5, 3 kilograms per day of iron removed from the total loading. It was somewhere around 12 milligrams of concentration. Then you have to take a concentration times your flow rate. That's what your actual loading is. So that's where you're really looking at it. And that loading is where you really start looking at efficiency. That's why you want it to go faster. And I wanted to point out that our next webinar, because as we're wrapping up here in just a few moments, will be in February. And we hope to be releasing more data because we've got about 5 or 6 data sets right now. We'd like to have 10 to 12 before to really know what's going on and really have good comparisons for statistical significance. So that's why we're holding off for right now. But the cleanouts, as we're doing them, are becoming more efficient as we upgrade the manifold. So that instead of every couple weeks, every 2 to 3, 4 weeks, that we're going every 4 to 6 weeks, 4 to 5 weeks, which then directly impacts your maintenance routine. And we're doing it in such a way that it requires basically a stick that's long and durable. You know, I've been using a piece of 2-inch, 10-foot long PVC. There are better things that could be used. We're also beginning to use pumps as well. And that definitely speeds up the process and gets you a lot more rigorous clean out every single time you do it. So we'll have a little bit more data. I'll know within the next month or so how much more effective that last clean out was versus just stirring it and draining it versus going in and doing the water injection. Want to thank Dr. Art Rose, Athena Chen, and her advisor, then Dr. Peter Heaney. Of course, I also want to thank Malcolm Crittenden with PADEP for finding the time and giving us letting us the dissolved oxygen probe. And of course, Anthony Taylor, the intern at the time, for all of his help. He was right there next to me, mucking these things out, you know, getting dirty and loving bioremediation. So it looks like we've got just a couple minutes left. Does anybody have any questions? Let's see if we can go to there's the chat section where audio, webcam, polls, handouts, attendees. Boy, there's a question section in here somewhere. I was pretty sure. Dashboard. Oh, there's a couple questions. Although I guess I already have them up, and the questions then are mostly just affirmatives that everything was going through okay. Yeah, so just a minute or two left here. Now's the time to ask any questions. Please, by all means, I'm watching the chat bar. And should there not be any more questions, I certainly thank you very much. We'll be coming back here to do, I want to do 2 more webinars. One I said January or February. We're hoping to get an entire year's worth of operation out of the system so that we can really compare dollars to donuts. Some of the things we're mainly looking for is, all right, when it gets colder, are we going to see any significant drop off? Now, when I did the pilot study in 2015, those were rates January, February. There's times when it was getting down to darn near 0. And we're still seeing 20, 30, 40 milligrams of removal. So it's hard to say whether we're going to see any significant drop off. You would think that you would. So that's one of the things we'll be looking for. Also hoping to do some more adaptations, get some more water running through that system, trying to get us closer to 70, 80, 90 gallons a minute. And also we're going to continue to adapt the manifold system to do better cleanouts, more efficient ones to increase the time between maintenance cleanouts. Okay, yeah, I don't see any other questions. So to everybody, oh, here we got one coming up from Earl. Which metals do you think the units are going to be able to remove? Well, we've done iron, aluminum, and manganese without any issues. Now moving into heavy metals, and thank you, Earl, for the question. Moving into heavy metals, we hope to be able to do lead, zinc, copper, eventually uranium maybe, and we're starting to look at some precious metals as well. So within the range of acidified or hard rock drainage, that's what we're looking for moving forward. In the area where we are right now, iron, aluminum, manganese, that's what I've got to deal with. And then we're also starting to look at selenium, which is another major issue both for drier areas and in some spots here in Pennsylvania and especially down in West Virginia, because that's some nasty stuff, selenium reduction, that is. Yeah, that looks like everything. If you have any other questions, please feel free. If you want me to do a site visit or even just get on the phone and chat for a little while, totally happy to do that. This is Colin Lennox with Biomining Products and Andy Gentry, and signing off. Thank you very much.